And then we can use DM setup, which has this hugely complex syntax. But anyhow, start, size, we want to use the crypt DM target algorithm, the abbreviated key, something, something, loop, something, pipe, DM setup. And since we don't have the problem with the null bytes or the cutoff key lengths and stuff like that, this should work like right out of the box. No problems at all. So, what about LUKS? Well, as I said before, LUKS stores a small header right before your encrypted data. And this header contains information about your encryption scheme, let's say that. But from the kernel point of view, it doesn't see that. It's just a keying program used to input the right key. So it uses the offset feature of the DM layer in order to jump past the header with the cryptographic information in it, and that is and just the rest of it is your encrypted partition. The offset is stored in the struct. See, we can find it in the key storage. It's there it is. No, that's Ivy offset. Well, it's there somewhere. Anyhow, the software I wrote to do this actually outputs the offset, and the offset is calculated in 512 bytes blocks. So we have to offset when we try to access this partition. We do this with LR setup. That's the easiest way. We could do it straight with DM setup, but that's a bit complicated because we have to recalculate the size and stuff. So we simply use LR setup with a -O option, which is offset, multiply the number we got from key search by 512, and input it to LR setup. Then we use the BlockDev software again to get the size of the device, and then we repeat the same thing. Echo, start, the size that we want to use, the crypt DM target, the algorithm, abbreviated key, something I don't know what it is, the device, something else. Then DM setup, create volume 1. That's it. It's not harder than that. So, what can we conclude from this little expedition into the crypto key world? Well, it's surprisingly easy. It's very, very easy to find and reuse your keys. All disk encryption systems are equally exposed. It's the same thing. You have to store your key somewhere, and when you're doing it in software, you have to store it in memory. Kernel memory will never be swapped out, but if you're using one of the userland encryption functions like CFS, you always run the risk of actually by accident writing your cryptographic key to your disk. But from a kernel perspective, it shouldn't end up on a swap at least. Don't lose your memory. That's very, very important. If someone actually is able to get hold of your kernel memory or a memory dump of your entire memory, they will be able to access your encrypted file systems. It's not difficult, it's very easy, and you'll have to make sure that no one does that. So, half an hour, perfect. Memory imaging techniques. When I wrote my paper, I had the assumption that you have to start out with a memory dump and you have to get that somehow. And during all of this, I started thinking about what kind of ways one would be able to acquire someone else's memory. How can you dump someone's disk, someone's memory without them knowing? How can you lose your memory without knowing it? So I did some research on this as well, and this is a well-researched area. Let me tell you that. There are a lot of people doing research in this area, and it's scary stuff. First of all, we have software imaging. Most modern operating systems like Unix and Windows and Mac OS X and everything else has like pseudo devices that allows you to access all of the physical memory. This of course requires root privileges, but still you can access all of the memory. Then we have like hibernation files. If you have a normal computer, it has a fixed size battery, and when it runs out of battery, it has to do something. And one of the options is writing the entire content of RAM to disk into a hibernation file that allows it to come back up again. If your cryptographic keys is in that memory, they will end up on your disk. And if I steal your laptop and I know that you have hibernation on, all I have to do is wait, because I know it's going to write its memory contents to disk. So that's just a waiting game. I was at the CCC Congress this year, or last year, and there was this guy who talked about Mac OS X. And Mac OS X did something really smart. When it wanted to hibernate, it encrypted the hibernation file. But in order to restore the hibernation file, it also wrote the crypto keys to disk as well. So kind of stupid. Some specific types of platforms has different kind of firmware breakpoints, particularly the Spark platform. So you can actually press this magic key combination on your console, and everything holds and goes into this firmware where you can play around with it, and you can dump your memory. Linux has the magic sysrequest keyboard combination, and from what I've heard, you can actually dump the memory from there, but I haven't verified this myself. But you always run the risk of someone doing this on your computer. And then, of course, we have the whole scene of virtualization software. When I did my research on this, I used Xen and just saved the content of my Xen virtual machine into a file and read the file, the crypto keys from there. But there's a whole lot of other type of virtualization software out there that people use. Xen actually has this wonderful live migration thing where you can send all of your memory across the network to another machine. Sounds wonderful, doesn't it? And if you set up that wrong, or if you set up it unauthenticated, someone can dump your memory from remote. Not very good. So software imaging technique is a threat, even though it is a bit more complicated, or it takes physical access to the machine in most cases. But let's face it, don't use crypto in your virtual machines. And then we have the whole area of hardware. There are some guys who built a custom-made PCI card that you can put in your machine to dump memory. They could hold the CPU and then do DMA access to all of the memory and dump it. One glitch though, you can't like insert a PCI card afterwards. You had to boot the machine with this PCI card in it. But on the other hand, modern platforms has hot swappable PCI slots. So you can like insert a PCI card in runtime. So if they get physical access to your hardware, they'll be able to input a PCI card in runtime. Then we of course have the option of custom-built PCMCI cards. The PCMCI bus, or one of the latest versions of it, has DMI access. So I could build a custom-made card, insert it into your computer, and have access to all of your memory. So is there any such card on the market today? Yeah, there is. I can buy myself a PCMCI Firewire card. I have one of these here. What do you think happens if I insert this into your machine, your laptop? Well, a modern computer will happily find this card and load the drivers for it. So I can dump your memory by inserting this card into your computer, given that you have drivers for this card. If we look at Windows, for instance, it will happily load the drivers. And on the other hand, I will have to pretend that I am an iPod in order to get DMA access to all of your memory, but it will work. Modern Linux distributions such as Red Hat, Ubuntu, Debian also have drivers for this card. So all of you who uses one of those operating systems and has the driver by default are vulnerable for this. I'm not really sure why the card needs the drivers, because it's a hardware thing to read the memory. It might be that if I buy a different card, I don't need the drivers, but I don't know. And of course, I could build myself a custom-built PCMCI card and read the memory that way. I don't need to actually pay the 12 euros for this card. I could spend $1 billion designing my own card if I had the money or time. And machines like mine, for instance, has Firewire built in to begin with. And my Macintosh here, it will happily initialize the FireWire card in the firmware when it boots. So I don't even need the drivers in my operating system for this to function. By the way, say the scariest part is definitely the PCMCI card. So disable your PCMCI port. Epoxy is a good option. Then we come to another different area. Residual memory. The same guy who did the research, I'm going to find his name, Wietse Venema at IBM, did an interesting test with IBM laptops. They created something they called stamps. A stamp was just a sequential number and a cryptographic checksum. And then they filled their memory with that. And then they rebooted their computer. Or rather, they did a lot of different scenarios, and then they checked how many those stamps were still in memory. So what if I run it as a web server for 14 days? What happens? How many stamps are left? And what if I reboot my computer? How many stamps are left? What if I turn my laptop off? How long does those stamps remain in memory? And this guy actually had a ThinkPad T30 turned off for 30 seconds, and when he booted it again, the stamps were still there. So I figured, let's try this on this laptop. So I wrote a small program that filled up all of the memory with a single string. I will Google before asking stupid questions. So it allocates 1 megabyte of memory, writes this string into all of it, allocates 1 megabyte more, and does it over and over again until it gets killed by the out-of-memory thingy. And then I just reboot it. Control delete, reboot, shut down, whatever. And reboots again into Linux with like init equals bin bash to like shrink the memory usage. And I grep from /proc kcore and grep for Google. How many here thinks that I got a hit? Yeah, you're right. The memory just riddled with it. It's everywhere. And it turns out that in the original IBM computers, when the computer starts up, it does a memory test. And this memory test includes writing different patterns to all of the memory, and then reading them back again, and then writing another pattern just to test that all of the memory is actually functional. But this takes a lot of time, and people don't want to wait for their computers to boot. So a lot of computers have this turned off completely, or they have it set to just do it when they do a cold start, or they have it set to only do on the like 641st case of the memory or something like that. So it doesn't actually do this all the time. So there's actually quite a good chance that if I get access to your computer, press Ctrl-Alt-Delete on it, boots from like a CD or a USB stick, that your crypto key will remain in memory long enough for me to actually read it. As long as I don't overwrite it, as long as I don't turn the computer off, it will remain there intact. DM setup, or like DMCrypt, has this really wonderful feature of removing the key or overwriting the key from memory when you deallocate the DM setup thingy. But when you press Ctrl-Alt-Delete on a normal Linux computer, it won't do that, because in the shutdown scripts, there is no shutdown script to remove your DMCrypt. So even if I do like a clean shutdown of your computer, it won't remove it. So you could remember that, like unmounting your crypto setup before rebooting. And you could enable the fully memory test if you want to. So, memory imaging conclusions. Physical access is very dangerous. If someone gets physical access to your computer, it's highly likely that they will be able to extract the crypto key as long as it's still turned on. There are a number of different venues that they could try, and they could try them in order. They could try with a PCMCI card first, then they could try to reboot the computer. Perhaps they could even like reset the computer. They can insert a PCI card if you have like hot plug PCI ports. I think that on a modern laptop you can even hot plug the mini PCI cards. So there's a lot of different venues here for actually making a forensically sound image of your computer hardware or computer memory.